So we're going to be working on this handout today. On Monday, we talked about a bunch of different aspects of NMR, but the main aspects that we talked about, let me throw a page in here. So the most important thing that we talked about was non-equivalence. And that's going to determine how many signals you see. All right, we also talked about the splitting pattern. Which you'll hear me refer to as the multiplicity. We talked about the chemical shift. Which is the location. And that's in parts per million. And then we talked about integration. And that integration is going to tell us the number of hydrogens each signal represents. All right, so if you understand those four things, it makes these spectra a lot easier to interpret. All right, so non-equivalence is going to determine the number of signals. The splitting pattern means that a particular set of protons is, you can determine how many neighboring protons are around that proton, or set of protons. The chemical shift, you can tell if it's in an electron-rich or poor environment, and then the integration is just the number of hydrogens. So we're going to start with these. We're going to start with number one. And before we do any of that, we're going to put the hydrogens in on these molecules. So I'm going to put in hydrogens on each one of these. So here we got two hydrogens on this carbon, and then two here. All right. Are any of those hydrogens equivalent? And what would you do in order to compare
them? Aren't the two like split on the same like V-shaped equivalent? Because they're on the same carbon.
Okay, that's good. Now let's see why or how we could tell them apart. All right, so I'm going to remove one. So I'm going to redraw this here. I'm going to put a chlorine down here for one of these. And then I'm going to draw it again, but I'm going to replace one of the other ones because this is how you compare them, right? So I'm going to put this here. Now I put a chlorine here. So I've swapped out one of each. Right, and you can see down here, I put a chlorine here, and then I put a chlorine here. Now, are these two compounds the same?
No.
No. And so if the two isomers you get are constitutional isomers and they're not identical, then that means that those two sets of protons are not equivalent to each other. Right, that's the test. Pull a proton. If you want to compare any two protons in a molecule, replace them with a different atom, replace one of them with a different atom, and compare the two isomers that you get. So these are two totally different compounds. This would be 1, 2, 3, 4, 5 carbons, 3 chloro, 2 pentanone. And then this would be 4 chloro, 2 pentanone. Sorry about that. Two different compounds. Are y'all following that? So anytime I want to compare protons, I just pluck one off and put another atom in its place. And then the other place where I want to compare it to, I do the same thing there. And the two isomers, if they're not identical, then those two are not equivalent, right? Just by the same token, the CH3s here and here are not equivalent. Do y'all agree with that?
Yes.
Yes.
All right. So now this compound should give me, and I'm gonna write it down here.
You kind of about to get punched.
Right. So this compound should give me how many signals? How many? How many?
Yo, what the shit that you're doing?
How many non-equivalent protons are there in that molecule, or how many sets?
Two sets.
What about the protons here and here?
That's wait.
She was talking about the one on the bottom.
Yeah, so all of when I say set, now I mean the protons that are on the same carbon, the same. So the two that are on this carbon right here. Let me just highlight that. So you got a carbon here, 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 and here with protons on it. So that's a set. A set is located on the same carbon. That's what I mean by that. So you got 4 sets of non-equivalent protons. So you should get, for that molecule, 4 signals, right? Because the number of signals is going to be determined by the number of non-equivalent types of protons. Is that right?
Yes, I have a question.
Go right ahead.
So when you comparing equivalency, you're comparing like the hydrogens on separate carbons as one.
Yes. So remember, these are heterotopic. Remember that term from Monday?
Yes, sir.
So these are heterotopic. And then if I'm looking at one particular atom, like these 2 protons right here on the same carbon, these are homotopic. Right? But compared to the rest of the molecule, they're all heterotopic. Make sense?
Yes, sir. It makes sense.
All right, let's look at the next molecule. If we look right here, I gotta shrink that down. All right, let's put the hydrogens in. Hydrogen here, 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 and here. And then you got 2 on each one of these. And you obviously have a CH3 down there. All right, so in the chain, is anything in the chain homotopic?
Yes.
Yes,
The 3 at the end, 4 at the end.
Okay. Hold on 1 second. I need to upload this handout again. All right. So right here, are you saying that the protons in the chain are the same? Is that what you're saying? So these are the same as these.
No, those aren't the same. The two together are the same.
Okay,
Yeah.
okay, good. So you're saying the CH2s, each one of those is homotopic within itself,
Uh-huh.
but compared to the other CH2s, they're not the same. Is that what you're saying?
Yes, sir.
Okay, all right, good. That's what I was trying to get at. So in that chain, that's going to give you at least 4 signals. All right, if you can't see the handout, if you're on your phone, it's not going to show up. If you're on a device, you'll be able to see it. But I'm gonna post it one more time. But yeah, if you're on a phone, it's not going to show up. All right, but it's there. And it's also on Blackboard. You want to go and grab it. It's in the assignments folder and in the folder labeled spectroscopy. All right. So on the ring, we're going to say that everything in the ring is different. Because if you change any of these out with a different atom, you're going to get a different isomer for any one of those. Oh, hold up, that's the same color as the CH3. I don't want to do that. Come on, Russell, get your mind right. And that's almost the same color too. I gotta do better with these colors. All right, that'll work. All right, so in the ring, you're gonna get at least 4 signals. And then you got 1, 2, 3, 4 signals in the chain. So this, the NMR for this compound, the proton NMR, is gonna give you at least 8 signals. Now, when we get to it, you're gonna see that some of the aromatic stuff, you're not gonna be able to tell apart because sometimes those aromatic protons will overlap with each other. Like the signals will overlap. So you're not gonna be able to really tell those apart. But the chain, you'll be able to see without a doubt. All right. Any questions about anything? And again, anytime you have a question about whether or not, if you're comparing 2 types of protons, you want to know if they're different, pluck one of those protons off and put another atom in its place, like a chlorine, and then compare the 2 structures that you get. If they're not the same, then those protons are heterotopic. All right, let's go to the next one. What do you think? I got hydrogens here. I got one here. And then what do you think about those CH3s? Is there some symmetry there?
Yes.
Because they're sharing the same carbon, right? Oh wait,
They
no,
are. They are. And so when you have a situation like that, that isopropyl type motif, normally these are going to be homotopic. But if you want to test it, you can test it. All right, let's go ahead and do that too, because I like doing that. Oh, shucks. Come on, Russell. So I'm going to do this. I put a chlorine there. And then the isomer, I'll put a chlorine there. Are those 2 the same compounds?
Yes.
They are. All right. Those are the exact same compounds. If you were to name it, it would be, let me see how many carbons we got. Let's name it real quick. 1, 2, 3. So it's going to be, I'm going to start counting at the chlorine. So this is going to be 1, 2, 3. So 1 chloro, 3 propanol. Hold up, 1 chloro, 2 methyl, 3 propanol. right? And same here. If you started counting here, this is going to be 1, 2, 3, exact same compound, right? 1 chloro, 2 methyl, 3 propanol. All right. So that's an easy test to see if those two are equivalent, and they are. You see that. So how many signals am I going to see for this? And keep in mind, let me say this too about protons on heteroatoms, like the OH proton. Sometimes you'll see it depending on the field strength of your magnet. The higher the field strength, like if you get 400, 500, 600 megahertz magnet, then you're going to see that OH proton, but it's not going to couple, right? It's not going to follow the N+1 rule. So let me put that in here. So that the oxygen is a heteroatom, right? It's an atom that's not carbon. So heteroatom protons. Right, they're not going to follow that N+1 rule. Right, so even though it's next to 2 protons, when you see the signal is not going to be a triplet. It'll probably show up as a singlet. And sometimes it won't show up at all, right? Depends on the field strength of your magnet. So it may or may not show up. All right. So if, let's say with the OH proton, if it does show up, how many signals are we going to have?
4.
Okay, good. So 1 for that. I agree with you 100%. 1 for that. And then, of course, we already got the CH3s marked out. So that's a total of 4 signals if the OH shows up and 3 if it doesn't. So I'm going to say 3 or 4 signals. All right. And then let's do the last one. What do you think? I'm going to be quiet on this one to see if you're paying attention. Is anything equivalent in that molecule? Any protons?
No.
Everything is heterotopic. We got 2 protons here. Right, so here. Got protons here and here. So how many signals?
3 signals.
3 signals. All right. Right. So in order to tell, let's say the OH proton doesn't show up for 3, like compound 3. Oh man, I've got the numbers all covered up. But this is 3 over here. So that's compound 3, and this is compound 4. That's 1, and that's 2. So let's say, for instance, the compound 3 and 4 you're comparing, and they both give 3 signals. There has to be some other way to tell those apart, right? So what you have to look at is the splitting patterns, and then you can also look at some other spectroscopic data. I sent y'all a video on infrared, right? Infrared is a powerful tool because infrared is going to tell you what functional groups are present. So if you're comparing 3 and 4, and you look at the infrared and the NMR, the infrared is going to show you an alcohol stretch, whereas for compound 4, you're going to see a carbonyl stretch and not an alcohol stretch. So we're going to talk about that shortly. All right, so let's go ahead and look at the first spectrum. And we got 1, 2, 3, 4 signals. All right, and the only compounds up here that we had that gave off 4 signals was this one right here. I'm gonna paste that down here. So that one, and let's say for the sake of argument that the OH shows up. And so we'll get that one up. Will all it potentially give off 4 signals. All right. So first of all, we can rule out right away the alcohol. Crop that out. 1 second. All right, we can rule this out because in the infrared, which is down here, you do not see an OH stretch. The infrared would show alcohol somewhere up in here, right? It'd be a really broad stretch. You're gonna see it on one of the next examples. So that's out, right? So now what we need to do now is start assigning signals to protons. I'm gonna redraw that because it looks kind of messy. Right, so we can start assigning this. I'm gonna keep the colors brown, blue, and all right, so that way we can just color code the spectrum. All right, so let's start here. Let's start right here. How many? First question, where would that signal show up? Second question, what would the splitting pattern be? All right, so the splitting pattern, let's do that first. How do we determine the splitting pattern for that?
4n plus 1.
Is it 4n plus 1 or just n plus 1?
Oh, n plus 1. I'm sorry.
Yeah, so n plus 1. N for this set of protons will be what? Where n is the number of neighboring protons. Anything next door to it, to the left or to the right?
0.
0, right? And so n plus 1 will be 1. So this should be a singlet. So we know what the splitting pattern is, and we see a singlet, but we also need to know why it shows up at 2.18 or 19 or whatever that is, right? Because it's really close to 2.2. So why would it show up there? Anybody? If you remember from Monday, that NMR chart that we had, protons on carbons that are adjacent to a carbonyl, they show up anywhere between 2 and 3, right? So that's why it's showing up at 2.18 right here. So it's about 2.18 parts per million. All right. Questions about that? And if you look here, the little number over top, that's my integration. So that signal integrates for 3 protons. So it matches, right? It's a singlet. It's showing up in the right place for the chemical shift. It's showing up in the right place for a set of protons that are adjacent to an sp2 carbon, and the integration is 3. So that's the signal for that set of protons. Any questions about that? All right, let's go down to the CH3 down here. And remember, there are 2 protons on this carbon. So what is N for that CH3 on the end?
2.
Would it be 1? Oh.
as is 2, right? Because there are 2 protons next door to it. Is that right? The blue protons that are right here, those are adjacent to that. And so when you're trying to calculate N+1, what you're looking at are the protons that are on neighboring carbons. So for that CH3 right here, this is the one we're looking at. N is 2, so N+1 would be what?
3.
3, and it should be a triplet. Now, if you look in the spectrum, you actually got 2 triplets. You got one down at 2.4 and one down at about 0.85, right? So now this is why it's important to know where things are supposed to show up, right? The alkyl protons, like that one, are they going to be more upfield or downfield? Right, because you got 2 triplets. There's another way we can tell them apart too, but
Upfield.
they'll be more upfield, right? That's one piece of evidence to help us figure out which triplet is which. But the other one is right here. It's the integration, right? Look at the integration. This triplet has an integration of 2. So that means that's representative of 2 hydrogens. This triplet down here is an integration of 3. So that's 3 hydrogens. All right. So which signal do you think that, which set of protons do you think that signal represents?
The one at 2.4.
Okay, look at the integration again now. This is a CH3.
Oh, yeah, the other one, I'm sorry.
So that's 3 hydrogens. The one at 2.4 represents 2 hydrogens. So it's got to be this signal. It's further upfield, right? And the integration matches and the splitting pattern matches because it's a triplet. All right. Is it making sense?
Yes, sir.
All right. So we got those 2 signals matched up. Now let's go to, which one do y'all want to do now? The blue protons, or you want to do the green one?
The blue.
All right. So how many neighbors would that one have? Let me put that hydrogens in here. Oh, let me put over here that this is alkyl. So it's going to be upfield. All right. So for the blue, how many neighbors does that have?
5.
Good, good, good. So N equals 5, and then N plus 1 equals 6. So that's going to be a sextet. And it's going to be a little bit further upfield also. But then again, when you look at the integration right here, that's integrating for 2 protons and it matches, right? It's got 1, 2, 3, 4, 5, 6 lines. It's split into 6 lines. All right. That's just a zoom in of that signal so you can count the number of lines. Right. So this signal right here is representative of that blue set of protons. It's a sextet. It's got the right chemical shift, right, and the right integration. So you see again, these 4 things always going to dominate like how we interpret a spectrum. Where the protons show up, how many protons each signal integrates for, how many signals are present, right? All those things are going to dictate how we interpret this spectrum. And then how many lines each signal is split into. So those are my 4 interpretive properties or principles for interpreting, NMR. All right. So now we can kind of go ahead and select these. You can see that the integration is 2. And then for that one, N is what? How many protons are adjacent?
2.
2. So N plus 1 is going to be 3. It's going to be a triplet. All right, any questions about this spectrum? I want to talk about the infrared too, because down below, that's what we call an infrared spectrum. And I sent the infrared video as like an introduction, and hopefully we'll have a chance to go through infrared again, so to reinforce what was in the video. But for this compound, what we're looking for are 2 stretches, right? Because there are 2 dominant functional groups here. One is the alkyl chain, right? You see all those carbons, all the carbons linked together in a chain. That's the alkyl chain. And the second one is the carbonyl stretch. So I'm looking for in that compound, I'll just redraw it. So I'm going to have I'm looking for a carbonyl stretch in the infrared, and I'm looking for alkyl stretching, so the chain itself. Right, so the carbonyl, this is a ketone. I'm looking for the ketone stretch. That's going to be somewhere between 1700 and 1800 reciprocal centimeters. That's my units for infrared. And then I'm looking for alkyl stretching. It's going to be somewhere between 2800 and 3000. And if you look in the infrared, you see right away, and the alkyl stretching always looks the same. You see this little jagged looking absorbance right here. Right, that's your alkyl stretch. So that alkyl functional group is absorbing infrared radiation at that wavelength. All right, you see it's 2878 and then 2984. Right, and then the ketone stretch is going to be down here. That's my ketone. All right, so your infrared is also a way to confirm what you have. So we looked at the NMR, we matched up the signals, and then now we can look at the infrared and match up the functional groups. And we know definitively, like if we were making this in the lab from an alcohol, we were taking 2 propanol and oxidizing it up to the ketone. When we took the NMR, this is what we should see, right? We should see that, and then we should see the carbonyl stretch and the alkyl stretch. All right, questions? Any questions about that? All right, let's go to the next example. Let's do another example. So we have C4H10O. It says calculate IHD. We'll do that on a different example, on the last example, because we've done that before when we did in part 1 degrees of unsaturation. So we'll do that on the last example, just so I can explain what that tells you. All right, so this is my spectrum. You got 4 signals. We already looked at this one that gave 4 signals, and we said that this one right here had the potential to give us 4 signals. All right, so let's copy that and then paste it down here. All right. So the question is, how do we know that this is the correct spectrum, right? We got 4 signals. And remember I said the OH may or may not show up. So what gives this away is 2 things. We got the infrared, and I'm gonna look at that first. This big, broad looking peak right here, right? This is your alcohol stretch. Right? Some anywhere between 3,200 and 3,400 reciprocal centimeters. Hold up, let me fix that. Right? 32 and 3,400, and it always looks like that. Fat, it's a fat, broad looking stretch. And so that's how you can tell that there's an alcohol functional group present by that stretch right there. So we know that this is the right compound, right? And obviously let's go through all of the protons. Which ones do you want to start? What do you want to start?
The purple.
Purple. Okay, you want to start at the OH. So the OH proton, in this case, is showing up. And if you look at, again, remember, it's not going to couple. So regardless of what N is for that, it doesn't follow the N+1 rule. So is there a singlet in that molecule, in that spectrum, that you think could be the OH proton?
Yes. Close
Where
to
is it?
4.0.
Okay, so about 3.9.
Yes.
All right, so let's do that. I agree with you. We're just gonna put OH. All right, so that's done. Right, it's not gonna couple, and when it shows up, it does show up as a singlet. And you can look at the integration as well, right? It's integrating for 1 proton. So that's another giveaway. Now we have another proton, another signal that's integrating for 1 proton. Look at how many lines it's split into. All right, it's split into 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. You have a proton that matches that? What do you think? That would mean for that proton, which is integrating as 1. All right, so this is 1 hydrogen. What would N be for that proton if it's split into 9 lines?
8.
8. Do we have a proton in this molecule that fits that description?
Yes.
It has 8 neighbors.
Would it be the green one, the CH2?
Okay, so let's look at that. So that CH2 has, and again, this is not going to split with the OH. So that really only has 1 neighbor to the right of it. You see that? The yellow one, the one highlighted in yellow?
But what about the CH3? And those are too far?
Yes, has to be right next door. Now look at the yellow one though. Right? It's neighboring the CH3 here. Am I right? And the CH3 here and the CH2 right here. So it's going to couple with all of those. Is that right?
Yes.
Yeah. See, it's that hydrogen is on this carbon right here. So the carbon next door to that has 3 hydrogens on it. The one here has 3 hydrogens on it, and the other neighbor has 2 hydrogens. So that's a total of 8 neighbors. Right, so for that, N is going to be 8. N+1 is going to be 9. So that signal is representative of that isopropyl proton. So it's here. And the integration is 1. Right, so we're going to call that a multiplet because it's 9 lines. We could call it a nonette, but it's easier just to call it a multiplet. Right, anybody not have a problem with that one? All right, so we only got 2 signals left, and they're both doublets, right? But let's see how we can tell them apart. So now, first of all, we look at the heights. The heights are different. We got 2 doublets left on the spectrum. Is that right?
Yes.
And the height of one doublet is about 3 times the height of the other one. And let's look at the integration. This is integrating for 2 protons. This is integrating for 6 protons. All right, so where can I find, let's go to the one all the way furthest down. Where can I find a set of protons in that molecule that's going to give me, or that's going to integrate for 6 protons? What that means is that, because you can't have 6 protons on 1 carbon. Are you following me? So that means that that signal has to be representative of some equivalent protons. So where we find that?
The 2 CH3s.
2 CH3s. And do you see why they will be a doublet? Right, for that CH3N equals 1. Is that right? Because it's only got 1 neighboring proton on the carbon next door to it, the yellow one. Is that right?
Yes, so you wouldn't count it twice.
No, because they're equivalent. You only count it once.
Okay.
So you wouldn't get 2 doublets. What you would get is a doublet that's twice the size of what it would normally be. You see what I'm saying? So the intensity would go up and the integration would change, but you wouldn't get a doublet for each one of the CH3s. You get a doublet that's twice the size. That's why it's bigger than the doublet that's down here at 3.4. Does that make sense?
Yes, sir.
So N equals 1, N plus 1 is 2. This is going to be a doublet. And it's going to integrate, come on, Russell, for 6 protons. So that's what I got there. It's green. So I'm going to go here and highlight that in green. That's the green set of protons. And it's both CH3s represented by 1 signal because they're equivalent. All right, and so now the other doublet is got to be this one, right? Is that right? The green, the light green.
Yes.
This is going to be a doublet. Will not couple with the OH. Okay, so why is it so far downfield?
Is it because it's next to the alcohol?
Yes. So it's downfield due to its proximity to that oxygen. All right, and then the last thing here is the IR. We already picked out the alcohol stretch, and then there's nothing left really. Well, that's a couple of, I'll take it back, a couple of stretches that are important in here. One is here, right? What kind of stretching is that? Does it look any different than the other stretching, other infrared we looked at?
No. It's
So what type of stretching is that?
allylic.
Alkyl.
Alkyl.
Close enough, but well, not really. but I hear you though. The AL, we good. I'll take that. And then there's one other stretch that we need to know and commit to memory, which is this one right here. This is at 1041. That's a CO single bond stretch. Show up, they usually show up somewhere between 1,000 and 1150 reciprocal centimeters. All right, we got to stop here. I'm about 3 minutes over. Any questions about this example or the one before it or anything? All right, let me stop sharing and stop recording, and we'll pick back up on record button. We'll pick up on Friday.